Hi, welcome back. Brand new unit, Module 6, the kidneys and an overview of the urinary system. Module 7 is related, where we'll look at the kidneys in terms of electrolyte and fluid balance. But for this unit, it's sort of an overview, general structures and functions. So, basic abdominal pelvic view, anterior view. Most of this you should be familiar with. There's nothing new here. It's just an intro, but you can identify the abdominal aorta, the inferior vena cava, the kidneys, the ureters, the renal veins, if you had to, etc. So not much there. So let's look at some basic homeostatic functions of the kidneys first. Kidneys are hugely important for maintaining homeostasis. Without kidney function, days of life are numbered less than a week, 3 or 4 days once the kidneys shut down. So they do a tremendous amount for maintaining homeostasis. So hopefully you gain an appreciation of what that is sort of looks like from this introduction. So let's just go through these functions sort of one at a time. There are 6 of them. First one, regulation of extracellular fluid volume, or the fluid load. And you should already have a pretty good grasp that fluid load, we're talking about blood volume, and that has a direct relationship with blood pressure. Generally, the more fluid, the higher the blood pressure. Drop fluid, drop blood pressure. Okay, so kidneys maintain that ECF volume by regulating urine output. Another major function is that the kidneys regulate the osmolarity of the blood. And osmolarity is just a measure of the solutes. So if you have increased osmolarity, you have increased solutes in the blood. And this sometimes happens with dehydration or overhydration. You either concentrate the solutes or you dilute the solutes, depending on state of hydration. But in general, the blood osmolarity is about 290 to 300 milliosmoles. So if you want to just make it easy, just remember 300. That'd be good enough. It's close. And the osmolarity of the urine can range anywhere between 50 and about 1200. So again, in terms of osmolarity, urine with an osmolarity of 50 is very dilute. And with 1200, it's very concentrated. And I should say that the units here are milliosmoles. We're not going to worry about defining milliosmoles as a unit, but you can in chemistry. For this class, it's a measure of concentration. That's good enough. The higher the osmolarity in milliosmoles, the more solutes in a given volume. So blood is about 300 milliosmoles. A third function is regulation of ion balance. And basically what the kidneys are doing is they're balancing sort of intake versus loss. You're always losing water and ions from the body, so if you're going to maintain balance, the intake is essentially equal to the loss. And sodium is the main ion that determines the ECF volume. So some people are very sensitive to sodium intake. They eat a bag of potato chips, the next day they weigh an extra 3 or 4 pounds, which is just water gain. So sodium, you remember from Biology 109, and osmosis, water follows sodium. The same happens here. Now sodium, as we'll see a little bit later on, is regulated by 2 hormones. ANP, which is our old friend atrial natriuretic peptide, and aldosterone, that we've also seen before. So those two hormones are going to be involved with regulating sodium balance. We'll get to that later. Another key ion that's regulated by the kidneys is potassium. And what I would like you to remember is that the potassium in the ECF is very low. Very low potassium in the ECF, in the extracellular fluid volume. Most of the potassium, you'll recall, is within the cells. So, if we have a little bit extra potassium out in the ECF, or a little bit less than normal, that's significant. And I don't know if you were introduced to this idea in Biology 160 or 241 of hypo and hyperkalemia and how that affects the RMP. And I'll get some feedback from you all this quarter, spring 2020, and I may do a little short video on that to go over how hyper and hypokalemia affect the resting membrane potential. It's significant, and you ought to sort of appreciate the relationship. So we might come back to that. But potassium is also regulated by aldosterone. So aldosterone is regulating both sodium and potassium through mechanisms we'll get to shortly. And a third ion, that's important ion, that's regulated by the kidneys is calcium. And calcium affects muscle and nerve excitability. That you should remember, and it works by adjusting the threshold up or down. So if I can sort of draw this in, just to remind you what we're talking about with a threshold. You remember this picture from earlier where we had a resting membrane potential, RMP, and this was, let's say, move my arrow a little bit. This was at, say, minus 70, and maybe this is, I don't know, 0, and this is millivolts. And somewhere in here, let's say, is, I don't know, maybe minus 50 was our threshold. And the membrane had to depolarize to threshold in order to fire an action potential. So if the membrane depolarized just a little bit and did not reach threshold, no stimulus, no action potential fired. But you can see that if you adjusted this threshold downward through altering the calcium level, you'd have lowered the threshold, and that original stimulus would now have generated an action potential. Likewise, you can raise the threshold, depolarize, but essentially increase the distance between the RMP and the threshold. So that's what we're getting at when we talk about excitability by regulating the threshold. Now, calcium, remember, was regulated by parathyroid hormone. We did that in ANP1 when we were looking at bone mineral homeostasis. And parathyroid hormone was released by the parathyroid hormones, and it targeted the osteoclasts, stimulated the osteoclasts to degrade bone, which dissolves the bone and puts the calcium back into the blood. And then that raises the serum calcium level. Okay, next slide. Several more functions for kidneys. Regulation of pH is very important. And the kidneys do this by regulating absorbing or excreting hydrogen and bicarbonate ions. So the 3's on the bicarbonate were supposed to be subscripted. So think about what happens here if we are regulating pH in the kidneys and we excrete hydrogen and we retain bicarbonate. What's that going to do to the pH? So think about just getting rid of hydrogen, lower hydrogen ion concentration, and that will raise the pH. Conversely, if the kidneys retain hydrogen and excrete the bicarbonate, we add more hydrogens, and that will lower the pH. And don't forget that the lungs can do the same thing. Remember the reaction in the lungs where carbon dioxide and water makes carbonic acid, and that reaction is occurring in the red blood cells as they are transporting carbon dioxide. So increased breathing, remember, will lower the CO2 level, will lower the acid production, which will raise the pH. And so the lungs are rapid. If lungs are failing or are compromised, kidneys may take over. Another function of the kidneys is excretion of wastes and foreign substances. So some of the wastes may include things like urea, nitrogen. Urea is how we get rid of nitrogen. Oh, various other metabolic wastes. Perhaps you mentioned creatine, or creatinine, however you want to pronounce it. And that was supposed to be under wastes. Sorry about that. And foreign substances, things like drugs are cleared from the body. Some of those are cleared by the kidneys, some are cleared by the liver, some are excreted with the feces. Those that are excreted by the kidneys include drugs and, importantly, antibiotics. Kidneys are very good at removing things that aren't normally in the blood, like an antibiotic. And we'll get to that mechanism of how they clear those substances from the blood shortly. And then a couple of hormones that are produced in the kidney. So I left the blanks here for you to practice filling them in. So it's the hormone that is targets. So we're talking about hormones that are produced in the kidneys. That's what the unit is about. So what's the hormone produced in the kidney, targets the red bone marrow, and promotes erythropoiesis? Erythropoiesis, or EPO. And another hormone that was produced in the kidneys that indirectly affects water balance, ECF, and blood pressure was renin. So do you remember how renin works on the sodium balance? This takes you back to RAS. And one of those A's is for aldosterone. Now be clear that aldosterone is not produced in the kidneys. Right? Renin is produced in the kidneys and stimulates indirectly the release of aldosterone from the adrenal cortex. So you might want to go back and make sure that you remember RAS. That's an important system that I will ask you to remember throughout the quarter. And the final hormone we could mention is calcitrol. Calcitrol is a steroid hormone, and it's involved with the synthesis of, basically is a final step in synthesis of vitamin D and calcium absorption. So it's a steroid hormone. Okay, so that gives you a sense of some major homeostatic functions of the kidneys. Next couple of slides are pretty easy, and we're just back to a general overview. At this point now, we're going to go into the anatomy. So you should be able to identify everything in this picture, and if I put some labels on here just for grins and giggles, you should be able to identify these as well. So for example, if I drew a little dot on that blood vessel and that's all you saw, you should be able to identify the red one. You should be able to identify the red and blue, which would be the renal artery and vein. The ureters are there. And then this is not a good picture, so I would not put a picture of this poor magnification. But there's also the celiac trunk, which is shown. And then there's this guy down here. What's that one? I'll let you figure that out. If you get stuck, let me know. I don't want to spend a lot of time on this right now. More detail, this would be a much better picture to ask you what some of these structures were. But you should recognize everything that's labeled in this figure. The adrenal glands, or the suprarenal glands, as they're sometimes called. The esophagus is shown. The hepatic veins that have been cut is shown. We'll come back to the hepatic system more with the digestive system. So those are the hepatic veins draining the liver into the inferior vena cava. And there's a hiatus for the esophagus for all three of these, and the aortic hiatus, and there's the celiac trunk again, that sort of thing. And there's a vessel that I asked you to identify on the other drawing. So that should be fun. So that's it for this short intro, homeostatic functions. The next unit we're going to talk about the peritoneum, the peritoneal membrane, and the mesentery. So see you then.